All right. Our next talk is from Dr. Ziran Wang. He is an assistant professor in the Lyle School of Civil Engineering. He also leads the Purdue Digital Twin Lab, which aims to build digital replicas of real-world entities. He was previously at Toyota Motors North America, where he led the digital twin roadmap for them. And his work has been patented, so he has over 50 patents, and he has also been featured at the CES as well. So today he's going to be talking about digital twins for connected and automated vehicles.
Thank you very much for the introduction, and thank you for the invitation. So during this talk, we just talked about trees, so we talk about buildings. Here I'm gonna talk about cars, which are more dynamic than those objects, and how do we build digital twins, and especially digital twin simulation for connected and automated vehicles. And this work has been done during my time here at Purdue, as well as during my previous time at Toyota. So what is connected and automated vehicles? What we are referring to when we talk about this whole concept of so-called CAV, right? Connected and automated vehicles. Probably more people know automated vehicle better. So automated vehicles are vehicles that have sensors, cameras, lidars, radars on those vehicles like those, and then they can operate by themselves based on their sensors. Connected vehicle, on the other hand, has wireless communication module that enable those vehicles to talk with each other, talk with the infrastructure, talk with the traffic signal, talk with the buildings, pedestrians. So those are connected vehicles. And if we combine these two concepts, and this graph came from US DOT, then we have connected and automated vehicles, which are vehicles that are not just driven by themselves, by their sensors, but also they are able to talk with each other through their wireless communication module. And we are eventually in the future, our mobility systems or transportation systems will be something like that, right? You have a lot of connected automated vehicles that are intelligently share the informations with themselves, with other infrastructure, with the buildings, with the train, and also satellite and things like that, and benefit this whole mobility in terms of safety, efficiency, sustainability. So it's a whole new world of traffic system or mobility systems that we were talking about. And specifically during this talk, I'm going to talk about how do we build digital twin simulation framework for connecting automated vehicles, and how do we leverage specifically the Unity game engine to build this whole holistic framework. So if you look at this picture down here, we have a physical world, real world objects, our traffic infrastructure, our traffic road network, all those different real entities, and also our vehicles, connected and automated vehicles that are sensing their data, that are sending their data to the digital world, where on the digital world, we reconstruct the environments, right? We build environment assets. So you see, this is actually a snapshot of the city that we built based on Mountain View, California, where our previous Toyota branch is located at. And we also build different vehicle assets, different vehicle models. Those are 2 out of many that we have, which are very realistic. They have the full vehicle dynamics. They have the full capability for driving and things like that. And we leverage specifically for this work, Unity scripting API that would build all those functionalities: scene generation, vehicle rendering, sensor simulation, driver interaction, which I'm gonna break it down in future slides. On top of those, we also built an external interface to allow this whole Unity scripting API to talk with external tools, because we think, just by the game engine itself, it has limited capabilities, but we want more, right? We want to generate the traffic through a traffic generator. We want to use all those fancy and complex add-on toolbox from MATLAB, or all those machine learning libraries on PyTorch or TensorFlow, and also leverage cloud computing from AWS. Then we build this external interface to allow this whole framework talk with external APIs. So I'm going to first talk about environments. How do we build environments for connected automated vehicles to simulate in this world? So multiple traffic environments can be created and simulated in a simulation. We build an on-ramp, because we work a lot on allowing different vehicles to talk with each other and collaboratively merge with each other on the ramp. So we build an on-ramp. This is based on the 237 highway in the Bay Area. So it's a 1-to-1 ratio. We build intersections. This is based on the SoMa area, south of Market Street in San Francisco City, where we have all these vehicles traveling through this intersection. We also have a highway scenario, which is more routine or standard highway, 3-lane highway that we're gonna simulate a lot of different car falling scenario, lane change scenario, and things like that. And you can see those are not really photorealistic, but it's good enough for us to learn the vehicle dynamics and then allow different drivers to test out the simulation algorithms that we have on those vehicles. And we also have weathers and vehicle types. As I keep saying that, this whole field of transportation engineering or traffic engineering, it's very dynamic. We have so many uncertainties, all those different variables, different weather, different vehicle types, and we want to model all those in a simulation. So you see this sunny weather that we modeled. We have foggy weather, which is pretty common in San Francisco. We also have I don't know, that's light rain and snow weather and storm weather probably, and all those different during the nighttime, during the daytime, and not just the weather. You can also see the difference, right? This I think this is Lexus RC, so which is a sporty coupe. This is more like a family friendly Toyota RAV4. So those different vehicle types are also modeled in a simulation or in a digital twin that enabled us to learn the dynamics of different vehicles and test out how different drivers drive those vehicles in a different manner, right? Probably this is more like sporty, that is more laying back. And we want to also learn the driving behavior and how do they interact with those connected automobile vehicles. Sensors, when we talk about connected automobile vehicles, sensors are essential, right? That really makes a difference between those fancy vehicles with the conventional vehicles we're driving every day. We also model the different perception sensors in the simulation in digital twin that with built-in features and third-party packages. So you see RGB camera, we learn the cameras, install all those different functionalities of cameras and run all those object detection, object tracking algorithms in a simulation. We also have depth camera on top of RGB camera, which can provide us depth information. We also simulate radar to have, you see all those 4 different radars that can sense different range and different angle of the objects surrounded by the vehicle, and also LiDAR, right? Light detection and ranging sensor, which can also sense the surroundings, and which is very similar to what we have in the real world. And I will show what we have in the real world in the last slide. And driver interaction. So this is something that, we actually build as a major contribution, because a lot of simulators out there, they only provide some like bird eye view driving, which are not that realistic. I mean, you can simulate some of the driving scenarios, but if you drive a vehicle in a simulation from the bird eye view, like a racing game, then it's not really that close to your driving experience. So we also build a driving interaction platform, which allow us to, to professionally drive the vehicle and make it also portable and plug and play to any places that we go to. So this was our setup back at Toyota, where we have, surrounded all those monitors. Those are old setup, to be honest. This was like 2017 setup, and we use this ever since. This was the setup during one of our collaborators, with one of our university collaborators, that they just have 3 TV monitors and they're surrounded by this racing chair. We just had the same setup right in my lab in Purdue building, pretty much the same setup, and allow the driver or the students to just get in and drive the vehicle and interact with other CAVs in a simulation. And this is actually something more interesting. Back then, ever since 2020, our office in Toyota started to work from home. I think they are still working from home. So I have to move this whole setup to my home, but just using my monitor, and I can just plug in and play this Logitech thing to my computer, to my laptop in 2 minutes, and then ready to go. I don't have to change any configuration. And we actually also sent this out to one of the remote interns that we have all the way in Vanderbilt University in Tennessee. And then she was able to also plug and play and then test out this whole simulation for CAV in a very short time. So the key concept of this is we can make this as fancy as possible. We can also add some dimensions for the seats, like vibrating yaw, pitch, roll, but we can also make it very simplified, just like this on your office desk, and then you're able to test your algorithms in a simulation in digital twin. So this is one of the video that one of the scenario that I just showed earlier for on-ramp merging. So the key concept is, we have a string of vehicles that are traveling on the freeway. If those vehicles, because they have the right of way, they don't have to show any courtesy to the merging vehicles. If they don't show any courtesy, then it's taking forever, probably, or taking a lot of effort for the ramp vehicle to merge in, right? And probably we all encounter this kind of scenarios every day during driving. But what if those vehicles, they start to talk with each other, they transmit their speed, their acceleration, their position with each other, share the information with each other, so they can collaboratively merge with each other. Probably this second vehicle on the main line, I know, okay, there's a vehicle trying to cut in front of me. Why don't I just show some courtesy, right? Show some gesture, decelerate a little bit ahead of time to create that gap for that vehicle, so that vehicle can merge in safely, smoothly, without any hesitation, without any risky behavior. And probably for my vehicle, if I'm driving that red vehicle, I can also adjust my speed, acceleration ahead of time, so I can catch up with that first vehicle. And then at the time that I'm actually at the merging area, I can just conduct a simple lane change behavior. So there are a lot of algorithms running in the background. That's what I'm working on, motion planning, motion control algorithm. That this whole digital twin simulation provides us the tool to actually test out this algorithm without actually going out in the field to do some risky scenario testing. This is another scenario. I showed the intersection. This is somewhat a more, I would say, a fancier scenario. We have the so-called augmented reality-based head-up display, where we showcase other vehicles crossing from other lanes on the windshield. And it's more like a AR type of thing. And this is actually a non-synchronized intersection. So we don't have any signal, we don't have any stop sign, but it's all based on the vehicle-to-vehicle communication, where all those vehicles talk with each other, share the information with each other. And then I'm gonna, if I'm the driver, I just drive my vehicle to stay in the green zone, avoid going to the red zones, because red zones are taken by other vehicles, and then I'm good to go. I can cross intersections without any full stop, without any hesitance, without any, wasting time and fuel at the intersection. This might sound and might look creepy, but if you think about this in your neighborhood, right? You have a four-way stop sign, and then you have no vehicle around you, right? Probably at the midnight, and there's no vehicle around you. But if you know, say, based on the vehicle-to-vehicle communication, I know there's no vehicle around me, then I don't have to waste my time to decelerate, wait there for 5 seconds, 3 seconds, and go. You can just go without any hesitance. And this relies on a lot of assumptions. I know, perfect communication, driver compliance to the system, but the thing that I'm trying to show here is building this digital twin simulation really allows us to test this out before we're actually testing that out in the field, because we had actually a lot of pushback from the executives from Toyota, because car companies are more conservative. They don't want us to test this out, obviously, in San Francisco City. So we said, we test this out in simulation. We file a lot of patents, publications, and probably we're going to test this out in some track, closed loop track in the future. This is the last scenario application I'm going to show. I was actually, again, in my working from home setup, where if you look at this whole thing, this is the digital twin simulation portal that I built based on Unity. Those two consoles, this is an upload from my desktop, from my laptop to AWS, to the cloud, and that is a download from the cloud. So uplink and downlink, all those computations are not happening on my laptop. All this computation are happening on the cloud, and we're actually leveraging all this cloud computing, cloud storage resources to benefit this system. And the system in behind is running a so-called personalized adaptive cruise control, which the system is learning from my driving behavior, sending all this data to the cloud. And on the cloud, there is a digital twin of me learning all my behaviors. And then next time when I switch on my adaptive cruise control on the system will be personalized, will learn from my driving behavior, will behave exactly like I drive. So I will be more satisfied with the setting of the system instead of changing all these buttons on my steering wheel. Sometimes I don't like falling too close. Sometimes I don't want vehicle to cut in. But this system allows this vehicle to learn from my behavior through uplink messages, and then computation is happening on the cloud. and downlink messages are less frequent because we only need like once every 10 seconds for the upgrade of the model. And we have a snapshot of during the past minute what is our trajectory, and all those information are also happening and stored on the cloud to benefit this whole system. So here I'm gonna talk a little bit about what we are actually right now currently doing at Purdue. Simulation on the cloud leverages computing power and data lake to provide guidance to CAVs. Because a lot of people, they really sometimes from time to time they question us, why do you lead this cloud framework? You can do everything on your onboard PC, right? Do build a digital twin, whatever you want, do your simulation, do your modeling. But we want to really leverage this whole digital twin concept, learning from not just the current data, not just the real-time data, but also time series historic data that probably we store on a data lake, somewhere on the cloud, somewhere in the backend server at Purdue or somewhere else. And all those data that are captured, say, from other places, from other vehicles will be used, will be leveraged by the Eagle agent to take decisions, to make more informed guidance, predictions about the future. So if you have information 10 miles down the road and that segment of the freeway, what is happening right now, what has been always happening during peak hours on Tuesday afternoon, then you might be making more informed decision regarding which route you're going to take, right? Probably I'm not gonna go there and get stuck over there. I want to have a stop at the grocery store, have the gas station to avoid the traffic over there. So that's the power of data lake, not to mention cloud computing resources, right? If you upload all those information to the cloud and you just leverage the powerful cloud computing. So here's what we are doing right now. It's just a starting where we build, so this is a discovery center, if many of you are familiar with, and we build a 1-to-1 ratio of this whole area. I'm just showing probably 5% of the map that we have. We have all those buildings built. We're not that experienced in building digital twins for trees, but those trees are not that important for us. What we care about is those road curvatures, right? We want those vehicles to behave nicely in those road curvatures. And besides this map itself, it's just a simulation environment. We want to have synchronizations between the real world and the digital world, because what we envision is digital twin really empowers all those real world entities only if there is real-time communication in between. If my digital world is not real-time synchronized with my real world, then it's just a simulation tool. It's nothing else. So what we have is we provide sensor measurements from all those vehicles running in the real world to the digital space. We reconstruct whatever is captured by my vehicle sensors, by the roadside cameras. We're actually talking about installing some cameras in top of the building. And then that is happening, the simulation is happening, the modeling, computation is happening on the cloud in the digital campus, send the guidance back to the real campus, to the real world. But what is the object that is transmitting all those vehicles, right? So this is the real part, the real asset that our lab has, where we have a full-size connecting omni vehicles with all the sensors, with the drive-by-wire feature, and that is enabled by wireless communication, so we can upload all those information to the cloud, to the digital campus, and then in the digital campus, we reconstruct the vehicles, we reconstruct the traffic environment, the pedestrian that are crossing that roundabout, all those different details, and then making guidance, right? So we have leveraging the sensors, we leverage cloud computing resources, and then probably give me some guidance while I'm driving this vehicle from this lane right here, based on the digital twin that I built. I know there might be some pedestrians crossing in that lane. There's a vehicle trying to, go into the roundabout, whether that the vehicle is trying to keep going or just exit this roundabout. We're going to leverage all those cloud data, those data in the data lake that we can build to those different assets and then model their behaviors, make predictions. And we have real-time synchronization in between these two. So that's the main message that I'm gonna convey. This is the last slide, I think. All those things that I showed earlier is just a snapshot of what we envision the future of digital twin. This is actually from one of our recent publication on IEEE IoT Journal, where we envision the future of digital twin will empower our mobility framework by a lot of other use cases. So you still see this two-layer setup. Down here, you have physical space, human beings, we have passengers, drivers, pedestrians, vehicles, connected and automated vehicles, conventional vehicles, traffic infrastructure, traffic signal, roadside unit, and things like that. They sample the data, send the data to the digital space through a communication layer. And in the digital space, again, digital twin is more than simulation. We do all those 5 things, right? We store the data, we leverage a time series database, we conduct modeling, we build models for those, do simulation for sure, very important, apply some machine learning algorithms, and then most importantly, make predictions to the real world, right? What will happen for that pedestrian, what will happen for the driver, whether that driver is sleepy or not, what will happen for that surrounding vehicle. We make predictions and then send back to the real world for actuation. So that is the whole loop of digital twin that we envision, at least for mobility, where we have all those and we enable all those applications. Just some examples. We have done many of them, and we're going to do a lot more of them in the future. With that, I think that's it. Thank you very much.
Yeah, that was great. There's, I think 4 or 5 moments in there. I was like, oh my God. There was one point when you were illustrating a particular merge pattern. And I think what you were implying was that, the autonomous vehicle recognizes that not all the other vehicles on the road are autonomous and is behaving in such a way as to prompt a particular sort of a response from a human driver. And I thought that was just wild to think about. Because for the foreseeable future, like, in the other scenario you showed where there were no stoplights and we're just like tracking whether or not you're going to collide with something and it's deciding whether or not it's okay to go. That would work if, everybody was part of this new system. But for the foreseeable future, there's this sort of intermediate mode where there's gradual adoption. They have to sort of coexist in this more complicated intermediate state. What do you see the role of like that notion that, you have an autonomous vehicle that is driving an environment where it's surrounded by not autonomous vehicles. And instead of merely reacting to the sometimes irrational behavior of human drivers, but actually psychologically manipulating them to achieve a certain goal.
That's tricky, and that's difficult, right? That's always we get always questioned by those kind of scenario, whether you will be behaving as a kind of commander to the surrounding traffic to follow you. One very funny idea in our field is one of the way that you can regulate traffic on the freeway is you have a 3 automated vehicle block the whole road, so you're gonna regulate the traffic speed, right? But that's just some crazy idea. A proper way to address your question: if some of those vehicles that are not connected, they are not automated, they're just regular vehicles like we drive every day, we can leverage roadside unit. We can leverage, say, probably there will be some cameras on those light poles or somewhere over there that can sense what our other vehicles are driving and send those information to a connected automated vehicle. So I can still make informed decision about all the surrounding vehicle, and we can predict their behavior. So not just vehicle to vehicle communication, but vehicle to infrastructure communication can be leveraged. Yeah,
Yeah, great. Thank you.
Thank you.
So yeah, you mentioned that when the vehicle is moving, the data will be uploaded to the cloud, right? It might be with the help of some internet connection. Or what if the internet connection is lost, and how the data will be uploaded to the cloud, and how can it communicate with the other vehicles at that time?
Very great question. I'll tell you a fact before answering your question. So one of the tests that we did earlier, probably 3 years ago, when we just used our phone, the hotspot, 4G, I think it's T-Mobile, so it's not the best provider. We use the hotspot on the phone, allow the vehicle just to connect with the hotspot, upload information to the cloud, download from the cloud on the other vehicle. The end-to-end latency is 80 milliseconds, so less than 0.1 second. And that's on a crappy 4G LTE network back then. And if we're talking about 5G in the future, and if we're talking about all this other stuff, that would be more, promising. But to answer your question, if we lose communication, right? If in this part of roundabout, for instance, we don't have any serial communication, there are two ways. One is there will be some local wireless communication. Actually, in our field, there's a thing called dedicated short-range communication, which is more of a Wi-Fi kind of thing. So you don't have to get serial communication. You just connect to your router, just connect to another router on another vehicle, and then you can just transmit your message locally without going to the cloud, without going to any server. The second solution to this is, if that is not a very time-critical scenario, say you just want to get, or you just want to broadcast your traffic scenario here in this 1 mile segment to your upstream traffic, then if this segment you don't have any communication capability, then you just store that on your edge computer. You do some edge computing, and then probably next time when you go into a zone that you have communication, you upload that to the cloud. So there is, some concept of anytime over-the-air update where you lose connection at some point, and then you just resume a connection at the other point. So there are many alternatives to this question, but again, that is very critical. Communication is very critical to all these applications. Yeah. Thank you for the question.
Two more questions. So,
hi. So how is the security on this thing?
Yeah.
And then, paranoid in me from both privacy aspect. And what about, I'm gonna jam that car signal and let it run into you.
Yeah. That like this question, and that is out of my domain. I'm not working on security, but we have a lot of security experts at Purdue that I'm sure. The privacy thing, that is actually what we're working on. We also, leverage a lot of so-called driver monitoring application. My students are working on using in-cabin monitoring camera to kind of monitor whether the driver is sleepy, whether the driver is distracted, and then we want to model this behavior to better inform surrounding vehicles. But there is a privacy concern, right? What if I don't want to give away all this camera data to the cloud? Like for example, I use Allstate Insurance. There's so-called DriveWise program. They monitor all your trajectories, right? If you open the app, they know all the places you go, right? They know where you live. They know where you go to your gas station or grocery store. One potential approach that my students are working on is to leverage federated learning. So instead of uploading all this raw data, camera data, whatever data, sensor data that you have to the centralized server, you do some edge computing on the edge. You kind of encrypt all those data, and then instead of sending the raw data, you send the parameters, the encrypted parameters to the cloud. So on the cloud, only the authorized user or authorized people that will have access to your data. And those are just parameters. Those are not your in-cabin monitoring sensing, and then decrypt all those. So in leveraging this federated learning, we protect the privacy, but also we reduce the communication requirements, right? We don't have to send all those LiDAR data, point cloud data. So that's one part of it. But for the malicious attackers, bad guys, that's something that I actually want to work with our professors here in cybersecurity. Yeah. Thank you.
And one last question from Zoom. So where do you think the main challenge in digital twin simulations is? So is it in the computational bottlenecks or the networking or the model fidelity?
Great question. I always have a slide at the end, which I didn't bring up. The challenges, I think the biggest challenge might be the data still. When you talk about digital twin, then you're really talking about building a virtual environment based on big amount of data. But what if you only have, I don't know, noisy data, low frequency data? How do you ensure your digital campus, in this case, still get real-time synchronized, still get 1-to-1 ratio, photorealistic or realistic or whatever that you're having happening in the real world, reconstructed in the digital world? So data, resolution, data accuracy, whatever that is combined in the data domain, I think that's still the key bottleneck. If we don't have real-time synchronization, if we don't have real-time data, then that is just some model. That is some simulation that you have. It's not a so-called digital twin in our understanding. So I think that's the answer to the question.
Thanks so much.
Thank you.
Thanks, Ziran, again.